Now let's do a couple of examples using the integrated rate laws. This example has the decomposition of this substance and says it is a first order reaction. We can see the reaction here, and it says that the rate constant is 2.8 times 10 to the minus third minutes to the minus 1. That's 600 Kelvin. It gives us an initial concentration, and then it asks us how long will it take for the concentration to drop to a certain level. So remember, there are two versions of the integrated first order integrated rate law, and I keep this table handy throughout the rest of my kinetics work. It says first order, so we have this version here, and in terms of natural logarithms, and then we've also got, well, let's see, we've got, I don't know, I tend to use this version here is one of them, and then we've also got our exponential version. And these two are totally equivalent equations. They're both the first order integrated rate law. One's just the exponential form and one's the natural logarithm form. And in particular, because we're solving for t, the version with natural logarithms is going to be helpful to us now. We'll see other ones where we're given t and asked for the concentration at some time, and we'll use the exponential version. So let's see if we can fill things in here. So we can just use A's, or we can use the actual substance that we're using. So we could personalize this for this problem by saying the concentration of SO2Cl2 at some time over the concentration at time equals 0 equals minus 2.8 times 10 to the minus third minutes to the minus 1 times t. And we'll then plug in our concentration values. Of course, the smaller number has to be the one that's at the time t, and here's our initial concentration. Good. So let's plug these in. I have 0.31 times 10 to the negative 3 molar equals the rate constant times t. And then let me get a number for this one on the left-hand side here. So this is going to be 0.31 exponent 3 minus divided by 1.24 exponent 3 minus. And then I get the natural logarithm of that. And I get minus 1.39 equals minus 2.8 times 10 to the minus third t. And let's see if we can keep it all on page there. Bring this over to the other side, and we get t is going to be equal to this minus 1.39. I'm going to just get rid of my minus signs here. Divide by 2.8 times 10 to the minus 3. And I get 495 as my number. And my units here, which I left out, are minutes to the minus 1, but then I bring it over to the other side and I get minutes. And you can see that the concentration units cancel out, so minutes are the only units that you get. And it takes 495 minutes to reach that concentration. Here's a companion problem. Look for the answers to be posted. Now, like I said, we're going to do some plotting for this, and plotting is going to help us determine the integrated rate law. And whenever we do this, we're going to have to make 3 plots, and I'm going to work through those plots and how to do it in Excel. Here's the problem. Plot the following data in Microsoft Excel to determine the rate law and the rate constant given the following data. And you've got the equation, or sorry, the reaction. You've got data for concentration of our reactant versus time, all very standard. What you're going to want to do is you're going to want to enter that data into Microsoft Excel. And once you get that data into Microsoft Excel, you're going to want to do 3 plots. You're going to want to do concentration versus time, natural logarithm of concentration versus time, and 1 over concentration versus time. You're going to do all 3 of those plots, and you're going to see which one is the most linear. So 3 plots. Which one is most linear? Whichever one that is, that's your integrated rate law, and that tells you also what your rate law is. And you'll see that the slope is going to be related to the rate constant for all 3 of these. Okay? And then if your question is, how do you tell which one is most linear? We're going to look at the correlation coefficient, the r squared value. And so r squared closest to 1 is going to be the one that tells us which one it is. And we'll tend to work with pretty well-defined data, at least in the lecture and homework portions of the class, but it's not always the case. And so this is a good way to determine, sometimes you won't even be able to tell looking at the data, but r squared, the correlation coefficient, is how we're going to do it. All right, so now let's go over to Excel, and we have to do concentration versus time. We also have to do natural log of concentration, so I'm going to put that in this column. So it's going to be ln of the concentration of peroxide, which is what this is. There you go. And to do the natural logarithm, you're going to hit equals. You're going to type in ln. You can see the natural logarithm function comes up. You're going to open the parenthesis, and then you're going to do the one next to it, and that is the natural logarithm of 2.32. Then you're going to come back over that one and put your cursor over the lower right corner. You can see the cursor change, and when it does, you can click and drag, and it will automatically reference the cell right next to it. So those are all my natural logarithms. Next, we said for second order rate, integrated rate law, it has to be 1 over concentration. And this is concentration of H2O2. There we go. And so you type the equal sign to tell Excel you're doing math, 1 divided by, and then click on the concentration. Same thing again, copy and paste that formula down, and now you've got all of your 1 over concentrations as well. What we can then do is we can then plot them all. I'm going to conclude my titles, and I'm going to plot them all by going to Insert. And the only one we ever do in this class is the XY scatter plot with points only. Here we are again. And we get 3 sets of data. And it might be nice to put our legend on here. Actually, let's make the chart as big as possible first. Oh, no, we don't. Yeah, we do. We need it. We do need legend. So legend, and then how about right? There we go. So we can see we have our concentration, natural logarithm, and 1 over for the different colors. And what you can do, you can make them separate plots. Or we can try and do it for just all on the same plots. Well, let's start with this. So let's go to our data for concentration. Now we're going to add a trend line. And I'll move this over here and move this up. So we have we're always going to be fitting lines to this. We're going to go down to the bottom, display equation, and display r squared. And for this line, so this is going to be for the concentration versus time. Doesn't look like it fits the data that well. Next, let's do our natural logarithm, which are our orange points, and add a trend line. And this time, again, linear, display equation, display r squared. And for the orange line, let's see, we'll just keep it down here by the orange line. We can see our r squared equals 1. Perfect. You can't get a correlation coefficient any more than that. This is essentially perfect data because I calculated it. Now, for a sense of completeness, and because it is oftentimes second order, although you can see this is a bit banana or curved shape, let's go ahead and add a trend line there. More trend line options. We come over, I won't show it this time, but I'm going to display and display. And you can see, let's see. Yep. There. So you can see that the r squared for the 1 over concentration is 0.92. The r squared for the 0th order is also 0.92. Those are worse. This is a perfect fit for the orange data, which is natural logarithm. That tells us that our fit is first order. And what you can do is you can you can put all of these on the same plot, though in the end, you can also, if I can do this, delete all the data that you don't want to see, and be left with just the equation that you want and just the line. So let's see. Oh, so now we have to determine from this the rate law. The rate law is first order, and the slope here, minus 0.0007. So natural logarithm of concentration of peroxide versus time was most linear. So our rate law is first order. Which means rate equals K times concentration. And K equals the negative of the slope, which equals, let's go back. We'll take away the minus sign, 0.0007. And the time was in seconds, so that's going to be seconds to the minus 1. I'm not really happy with 1 sig fig there, so I'm going to go back to Excel. I'm going to move my nice plot here, which I do need titles and things on. And I can see that the only data now being plotted is my natural logarithm versus time. And I want a better value for the K, for the slope of this. So I'm going to type in equals slope and open a parenthesis. And you can see it's asking for known y's, comma, known x's. So I'm going to highlight my known y's, hit the comma, then I'm going to highlight my known x's, close the parenthesis, and now it tells me that the slope is minus 0.00073, and I get one more sig fig, and I'm going to be happy with that. So I'm going to come back to my page here. Now it's 0.00073. We might also call that 7.3 times 10 to the minus 4th seconds to the minus 1. And this is the graphical method of determining the rate law, and it's a very powerful way of doing it, and you can bet you're going to be doing it in the future. Now, yes. So here are all my plots so that you can see, and I really strongly recommend that you do this. For this example, using the r² value, we can see them in some more detail here. And there's also a companion problem to give you a chance to do it. I'll be interested to see, and I will be posting this, what the results are for the 3 plots. And I bet there's one of these, if not more, on the homework or the different assignments for this course.